some. This is example 2 of our application of differential equations. So a bottle of soda at temperature 6 degrees Celsius is removed from a refrigerator and placed in a room at temperature 22 degrees Celsius. If after 10 minutes the temperature of the soda is 14 degrees Celsius, determine its temperature after 20 minutes. Now, according to Newton's law of cooling, the rate at which an object gains or loses heat is proportional to the difference in temperature between the object and its surrounding. So we can now say in our solution, let Y be the temperature. The temperature of the soda, at any given time. At any given time, after it is removed from the refrigerator. So according to Newton's law of cooling, according to Newton's law of cooling, dy dt, the rate at which the object loses now heat because it is now cooling, will be equal to a constant or proportionality multiplying 22 minus y. Multiplying 22 minus y. Because it is being placed in a room which its temperature is 22 degrees. So this is the way the temperature is changing from 22 to the present temperature at any given time, which is y. So the y dt is equal to k into 22 minus y. So our dy dt is k into 22 minus y. This implies what? We can separate the variables here. Dy all over 22 minus y is equal to k multiplying dt. We have now separated the variables. So the integral of 1 all over 22 minus y dy is equal to the integral of k dt. It's equal to the integral of k dt. So from this, when we integrate this, we'll get minus ln of 22 minus y. The integral of this, because when you differentiate the denominator, we get negative 1. Negative 1 is not there. If you input it, then there will be a negative out, which is that. Minus ln of 22 minus y is equal to kt plus a constant of integration, which we are going to call c. So from this, we say ln of 22 minus y will be equal to ln of 22 minus y is equals to minus, we multiply both sides by a negative, so we get minus kt minus c. Minus kt minus c. So 22 minus y will be equal to exponential minus kt minus c, which will be equal to e power negative kt multiplying e power negative c. That's 22 minus y. E power minus c is a constant. Negative c is another constant. So we can say this is equal to e power minus c. Let's call it a constant a. So this will be a e power minus kt. So 22 minus y is equals to that. Therefore, y alone will be equal to 22 minus a e power minus kt. Now we've gotten the temperature of the soda at any given time. But there were some conditions given that we need to use so that we can get the arbitrary constant A and K, so that we get a particular solution of the said differential equation. So we say when t is equals to 0, y was equals to 6. When t is equals to 0, y was equal to 6, because the bottle of soda was at a temperature of 6 degrees. That is when we started the process of that soda gaining some heat. So we say this implies what? 6 is equal to, we now go to this, is equal to 22 minus a. T is equal to 0. When t is 0, this one will also go. E power, k times 0 is 0, e power 0 is what? 1. So this implies our a. Our a will be equal to 22 minus 6. 22 minus 6, that gives us 16. 22 minus 6 gives us 16. So we've got an a. So this implies what? Our y is equals to 22 minus a e power minus kt. Power minus kt. So from this, we say this will be equal to 22 minus 16 e power minus kt. E power minus kt. Now, there is another condition which can help us get the value of k. We are told when t is equals to 10, y is equals to 14. When t is equals to 10, y is equals to 14. So 14 is equal to 22 minus 16 e power minus 10k. Because t is now 10. T is now 10. So from this we say now 16 e power minus 10k is equals to 22 minus 14, which is equals to 8. So e power minus 10k is equals to 8 all over 16. So 10 minus 10k is equal to ln over half. So k alone, it is minus 1 over 10 ln of a half. Minus 1 over 10 ln of a half, which can also be written as It is ln over half raised to a power negative 1 over 10. Negative 1 over 10. Which we can simplify further as k 0.0693. 0.0693. Therefore, the particular solution, the particular expression for temperature of that soda at any time t, after it has been removed from the refrigerator, is given by y is equals to 22 minus 16 e power minus 0.0693 t. 0.0693 t. And that's the value of k. This is the value of k we are now inserting. So we are told we would like to get the temperature after 20 minutes. Temperature after 20 minutes. So when t is equals to 20, when t is equal to 20 minutes, our y now will be equal to 22 minus 16 e power minus 0.0693 times 20, which is equals to will be equal to 22 minus 0.000015, which will be equal to 21.99985 degrees Celsius. Degrees Celsius. And that will be the temperature after the 20 minutes. So we have solved that. That's an application of first order DE, but on temperature analysis that is requiring Newton's law of cooling. Number 3, we have a circuit which now gives us its second order circuit. It will lead us to a second order differential equation. So the circuit shown below is switched on at t equal to 0. If the charges and currents were initially 0 before switch on, determine the expression for charge QOT for t greater or equal to 0, current I as a function of t for t greater or equal to 0. So in our solution, we use by KVL, by Kirchhoff's voltage law, a drop across an inductor is given by L di dt. Drop across the resistor is given by Ri. And drop across a capacitor. This is, remember, this is R, this is L, and that is our C. That is our C. Now, drop across a capacitor is given by 1 over C, the integral of I dt. And this one now should be equated to E, the voltage that we have. But because we are being asked to get the expression for charge first, we say, but I is equal to dq dt. Replacing for I, this will be LD dt. We have dq dt for I plus R dq dt. R dq dt plus 1 all over C, the integral of dq dt multiplying dt. And this is equal to E. This one simplifies to LD squared Q dt squared plus R dq dt plus 1 all over C multiplying Q is equal to E. This dt and dt cancel. The integral of dq, you get Q, which is this one. So inserting our values, we say this implies d squared Q dt squared plus R 160 dq dt plus 1 over C, 1 all over 10 to the power minus 4 Q is equals to 20. This implies what? Our d squared Q dt squared plus 160 dq dt plus 10,000. 1 divided by 10 power minus 4, you get 10 power 4. So 10 power 4, which is 10,000 K, is equals to 20. So this is the differential equation that in terms of K, that will represent the action of this circuit when this switch is put on or is closed at time t equal to 0. Now, we would like to solve for Q in that particular case. I would like to solve for Q in that particular case. So, this is a second order differential equation. We know our Q will be equal to what? QC plus QP. The auxiliary quadratic equation, as we can see from here, will be m squared plus 160m plus 10,000 is equals to 0. This one gives us m is equals to what? 1 negative 160. So m is equals to minus 160 plus or minus, and we have plus or minus b squared will be 25600. That is b squared and 60 squared. 25600 minus 4 times 10,000. 4 AC, 4 times 1 times 10,000, all over 2A. all over 2 times 1, which is equals to minus 160 plus or minus. This one we get J 120 plus J 120 all over 2, which will be equal to minus 80 plus or minus J60 plus or minus J60. So this is the value of M. So our QC will be equal to, e power minus 80t into a cos 60t plus b sine 60t plus b sine 60t. That is our complementary function for our Q. Let's now go for the particular integral. But we know d squared plus 160d plus 10,000. The whole of this, when it multiplies QP, is what should give us 20. So from this, our QP is equals to 20 is equals to 1 all over d squared plus 160d plus 10,000. The whole of this acting on 20. Here we are using the d operator method in getting our particular integral. This implies our QP will be equal to 20 is a constant, and now we have 1 all over d squared plus 160d plus 10,000 acting on 1, and 1 is the same as e power 0t. Applying theorem 1, where there is a d, we insert a, and our a is 0. So when we insert 0 here, we get our QP as 20 all over 10,000. E power 0t will pass. So this one is equals to 1 all over 500. That one goes here. 1 all over 500, that is our QP. Therefore, our Q as a function of t will be equal to QC, which is e power minus 80t into a cos 60t plus b sine 60t plus 1 all over 500 plus 1 all over 500. And that is the expression for our charge. But there are some arbitrary constants here, a and b, which we need to determine their values given the conditions that were stated. We know when t, we need a derivative of q. I, which will be equal to q prime over t. So when we differentiate this one, what do you get? When we differentiate this, we keep this one constant. E power minus 80t is constant. We differentiate this minus 60 a sine 60t. We are differentiating what is inside the bracket because we are keeping this one constant, plus 60b cos 60t plus, no, we differentiate exponential this, we get minus 80 e power minus 80t minus 80 into a cos 60t plus b sine 60t. Here, when you differentiate this one, you get a 0. So this is the derivative. So we are given when t is equals to 0, there were no charges, meaning q is equals to 0. This implies what? We are now substituting. We are now substituting in our expression for q. We get 0 is equals to 0 is equal to e power 0, 1. So 1 into a cos 0 is that. Sine 0 is 0 plus 1 all over 500. So this implies what? This implies our a is negative 1 all over 500. So when t is equals to 0, k prime of t, which is equals to I as a function of t, is also equal to 0. So in that expression, we say 0 is equals to 0 is equal to where there is t, we are inserting 0. So that is 1 into 60b into 60b. 1 into 60b. This one will be 0, this one will be 60b. Minus 80. E power that, it is minus 80 into a. So we say 0 is equals to 60b minus 80a, which is equals to 0 is equals to 60b minus 80 times 1 all over 500. So our 60b will be equal to 50, which is 4 over 25. 25 times 20. 25 times 2500, yeah. And 4 over 25. Therefore, B will be equal to 4 all over 25 times 1 over 60, which gives us what? 60 goes into 60, 15 times. So 25 times 15, 375. So this is 1 all over 375. Therefore, our Q as a function of t will be equal to 1 all over 500 plus e power minus 80t into a 1 over 500 cos 60t plus b 1 all over, b is 1 all over 375 sine 60t. And that becomes the particular solution, the expression for charge required in that particular circuit. And when the switch is put on, or when the switch is closed at time t equal to 0. That's the expression for our charge. We are still remaining to get the expression for our current that flows in that particular circuit. So because we have the derivative around, we can just replace for the values of A and B in the expression for I. The expression for I, we have it. So therefore, we can say I, as a function of t, will be equal to e power minus 80t. E power minus 80t into minus 60 a, which is over 500 sine 60t, plus 60b, 60 all over 375 cos 60t, minus 80 e power minus 80t into a 1 all over 500 cos 60t, plus 1 all over 375 sine 60t, which is equals to exponential negative 80t. We can have it here. Negative 80t. So this 0 and there, this is 3 minus 3 all over 25. That's minus 3 minus 3 all over 25 sine 60t plus minus 60 all over 375 cos 60t. Now minus 80 times this, we get minus 80 we continue here, minus 80 all over 500 cos 60t. Minus 80 over 375, we have minus 80 all over 375 sine 60t. When we add all this, let's do the addition. Get e power minus 80t into this one we have minus 1 over 3 sine 60t which will be equal to a negative a third e power minus 80t sine 60t sine 60t. And this is the expression for current as a function of t. That's the expression for current as a function of t. So we've answered that question fully. We've gotten the charge. We've gotten the current flowing in that circuit when the switch is closed at time t equal to 0. So there are so many examples on application of differential equations depending on the line of study. We have things dealing with the rates of reactions. We have things dealing with oscillations or vibrations. We have things dealing with rate of disintegration of a certain substance. So the application is large. So for now we can leave it at that particular point, since now you have known how to apply a differential equation in solving some circuits or in solving some problems following certain laws. So stop there.